All right, so we're gonna talk through some of the ideas with kind of describing motion. So our first one is just to kind of establish some ideas. So our first idea is like position, so where something is located in space. So we have a number line here, which is very convenient to describe where something is located. So if we are locating this object here, which is our smiley face, and I put it here at this location on the number line, you can clearly see it's at the 0 location, so it's at 0 meters. If we move it in one direction, maybe to the right, so the location would be at 5 meters, and it's to the right of 0, so we usually call that positive. I could also move it to the left section, which is the negative section. So location is just your position. If we're working horizontally, it's usually represented with an X. If it's vertical, we'll use Y. So distance is just describing the sum of all the lengths that an object moves. So if we start our person here at 0, and then we move them over to 4 here, so I'll draw a little arrow in. So if we go from there to there, oh, sorry, wrong thing. So if we draw a little arrow going to the right to represent, that's supposed to be an arrow, but it's not. There we go. A little arrow going to the right. There we go, finally. That it goes from 0 to 4. Our distance traveled would be just a positive 4 meters. So that would be in that case. If we kind of moved our object from this 4 position, going all the way back over here to negative 4, so this positive 4 was the first thing. We would go from 4 to negative 4. And again, we're just adding the distances, so the space between, so that's 4. And then if we go back the other way with our arrow, and I'm starting here at 4 and going to negative 4, that would be 8, because 4, if you count 1, 2, 3, 4, 5, 6, 7, 8, so that's 8 spaces. So that would be 8 meters for that second leg of the trip. And then all we're trying to do is put them together. So if we had 4 meters plus 8 meters, you get a simple 12 meters, which would be the total distance of our smiley face in that example. Um, so distance is a scalar quantity, which means it doesn't care which direction you're going. It's just counting steps. So if you imagine your car records distance, so it doesn't, on your odometer, it doesn't tell you which direction you're heading. It just says which, what's the total lengths all put together. For displacement, which is a similar idea, but it's describing the change in position of an object. So displacement is represented by a triangle and X. The triangle represents change in. You might have seen that mathematically before, and we'll bring it up again when we talk about graphs and slopes. So change in X would be the displacement. Change means you subtract, so it's always the final minus the initial. So if I start with this problem here again, and I just say, okay, oh shoot, trying to delete some of these things. Um, we're doing the same path here. We're still starting our initial position here uh, was xi for initial. That's where the smiley face started in the beginning, which was located at 0 meters. And we traveled to the right 4, and then we traveled back 8 to the left. Our final position, which is xf, we're gonna figure that out. So we'll write out xf for final, and that was at negative 4 meters. Drink up a little bit. So that was the location of this smiley face. And for the displacement, we just really care about from where you start to where you finish. So our displacement vector here, which I'm going to draw in a different color, is starting from here and going to where it stopped. So it looks like I moved 4 to the left, and that's what we should calculate mathematically. So for that, if I'm working through it, using our values that we had in our example here, it would be our initial position, which was 0, minus, and our final position was -4. So 0 minus -4. Um, I'm sorry, I said that backwards. So it's final minus initial. So -4, sorry, minus 0 would get you a -4. So it's the final position minus the initial position. So in actuality, the object moved, even though it went to the right first and then it went back to the left. The change in position is from where it starts to where it finishes. So it moved 4 to the left, or -4. Um, the negative and positive indicates the direction, so that's really important in our description of motion. So make sure that you are aware of that in in that in that aspect. So common units for distance or displacement: meters, feet, kilometers, miles, just appropriate for the length. And then again, displacement is a vector quantity, so it deals with direction. So again, more practice here. So it says, what's the distance traveled from the house to the store? Whoops, trying to grab the smiley face. So if we're starting at the house and we move to the store, it looks like the distance between there is going to be 3 kilometers um, according to the graph there, or the image. So 3 kilometers would be the distance. First answer. Then if we moved from the house to the post office, so if we started here and went all the way to the post office, that would be 6 kilometers, because we're taking in that entire trip. Um, if we traveled the distance traveled from the post office to the house, um, that would also be 6 kilometers, because it's just going the reverse direction. We don't care about positive or negative with that. So it's the space between those is the distance. And the total distance for the entire trip, if we started at the house, went to the store, then to the post office, and then back to the house, it would be 6 to the right plus 6 to the left. So the house to the post office and then back. So if we did that, it would be 6 going to the right plus 6 going to the left. So it would be 6 plus 6, which is just 12 kilometers. Um, so this is, again, this example is using distance. The next one is the same situation, it's just talking about displacement. So displacement, again, it involves direction. It's a vector quantity. So if we start with our guy or our smiley face at the house again, and he's going to go the house to the store. We're going to include the final and initial position. So this is the initial position. I'll just write a little I or XI for that. And then our store is the final position in our first case. So we're going to do the change in position, or delta x. So it's the final minus initial. So 3 minus 0 is just a 3, and it's a positive value. And that positive indicates, again, that you are going to the right. So that arrow is pointing to the right. So that's the displacement direction, which would be the positive direction, because right is established as positive. So so the answer for that one would be a positive 3 kilometers, or you could say 3 kilometers to the right. That's fine. For the next one, so that's what's the man's displacement from his house. So if we started at the initial position at the house again, all the way to the post office. So this time we're going to move from the house to the post office, and our displacement gets larger this time. So you should be able to kind of figure that out, that this one, very similar in terms of answers so far with the distance, but we'll see some subtle differences. This one's a positive 6 because it goes from the final position is, oops, the final position is now at positive 6, and it'd be positive 6 minus 0, which is still positive 6. So positive 6 kilometers, that's fine. The positive indicates going to the right, or you could just call it 6 kilometers to the right if you wanted to write out a little phrase afterwards to describe the motion. It says, what's the man's displacement from the post office to his house? So basically, we are flipping this arrow over. We're going the opposite way. And we're going to switch these two things. So the final position is now the house, and the initial position, um, xi, is the post office. So we're starting at 6 and we're finishing at 0. So this one I'm going to just show the math with because I think it's worth the time just to make sure there's no confusion. So for this one, our final position is 0, back off 6. So that's going to be a -6 kilometers. And again, the negative should indicate that it is going to the left. 6 kilometers to the, and I'll try to shrink this a little bit. All right. So the last one here is sort of an interesting question. And before we talked about um, the total distance traveled. Now we're going to talk about the total displacement. So again, displacement you calculate the same way all the time. It's the change in position. So it's the final minus the initial. So our initial position here, we started at the house. If you think about this, we're going from the house to the post office and back. So we started at the house, we moved all the way to the right to the post office. So that was like a +6 displacement. Then we returned from the post office going back to the house in the original position. So our original position, the xi, our initial, is the same as the final. So if there is no change in position, there is no displacement. So for this entire trip, the answer would be 0. So this is again where you see kind of the difference in the idea. So 0 kilometers would be the displacement, and that is because there was no change in position. They started and stopped at the same spot. So the distance was very different. In a lot of the cases, the distance was the amount traveled, but in the displacement idea, it involves the direction, and that can have an impact on your answer. So I'm going to stop there, and next time we're going to get into graphing position and time.